In this subVI, we implement the raised cosine pulse, which is expressed by this rather large equation. B naught and alpha are also defined here. Alpha needs to be a value that's just between 0 and 1. I'll begin by putting down the front panel controls for the primary inputs. And those include the bit interval, has a default value of 0.01 seconds. Alpha, called the excess bandwidth factor, sometimes also called the roll-off factor, has a default value of 0.5. The number of bit intervals for the support is capital N, has a default value of 4. I needed to change that also to be an integer type. And lastly, we have the sampling frequency with a default value of 1000 Hertz. And that's how we establish those as the default values. Now alpha needs to have a limit on its values of 0 to 1. Select the properties and then select the data entry tab and specify the minimum value as 0, maximum value of 1, and the increment of 0.1. And this way, when you use the increment decrement button off to the side, we see now it's going in steps of 0.1, and then it limits out at 1. Here it limits out at 0. Compare that to one where we've not done anything special. We see that it increments by 1. And we can also make it negative, which isn't physically appropriate for bit interval. Of course, if you wanted to take the time, you could say that the minimum bit interval is supposed to be 0 or some finite value. I'm going to recommend the MathScript node as the primary method for implementing this reasonably complicated equation. And to actually develop the contents of the MathScript node, I will also recommend that the easiest way to do this is the MathScript window. This is the interactive technique by which you can debug your M script. Once it's debugged, then you can drop that back into the MathScript node. Now, I'm not intending to really cover all of the syntax details of MathScript, but more what I'm focusing on is the general approach here. What I'm doing now is setting up some comment lines, and I'm also putting down the default values for things like sampling frequency and so forth. So I put these up right at the beginning. Kind of think of these as the user inputs. So for our development and debugging purposes, we could set these values conveniently within the MathScript window, and then later on we can comment out this section and allow the front panel controls to then influence these values inside the MathScript node. Now you can go ahead and save that as an M file to be retrieved later on. I'm going to go ahead and save that to the raised cosine pulse demo.m. Now my user inputs are above that dashed line, when I need to start operating on those user inputs, in this case I need to calculate the so-called Nyquist minimum bandwidth. That's the B0 term. So that'd be 1 divided by 2 times the bit interval. Now if we run the script, we see the results in the left-hand window. There we go. So here we recognize the user inputs, and then we also recognize the value that was just calculated for B0. Now we need the time basis, or what you might call the support for this function. I'll call this TT. You could call it just single T if you wanted to. But time is supposed to run from some integer number of bit intervals before 0 out to some number or some integer number of intervals after 0. So TT is going to be now an array, or a vector if you like, that runs from minus the number of bit intervals out to plus the number of bit intervals. The step size then would be our delta t, and that's the reciprocal of the sampling frequency. So we see for the choices that we've picked, we start at minus 0.04 seconds and go through 0.04 seconds in steps of 1 millisecond, or the reciprocal of 1000 hertz. Now it turns out that MathScript has the sync function built in. I encourage you to check the help page on that. And I'll give you the full details that you need to consider. Also, of course, the cosine is built in. Now some other considerations then, especially about performing the division of what amounts to be 2 different arrays. We need to do array-wise division. So we do that by specifying a decimal point or a period in front of the operator. So we'd say dot divide is the operation that divides those 2 arrays. The squaring operation, which also operates on an array, can be likewise expressed as, say you had a collection of terms, we'd say dot hat, that's our exponent operator. So that says do the squaring operation array-wise. So those are applied to each element in the array. Now to develop a little bit better sense of pulling the pieces together, or checking your work as you go, it's nice to be able to plot these expressions. So for example, supposing we wanted to just investigate the sync function by itself and make sure that's working properly. I'll point out that the semicolon suppresses the output. So if you didn't want to clutter up your window, you can use that as a mechanism for not constantly generating these array values off to the side, or the array outputs. If we then wanted to take a look at this function plotted as a function of t, we put down the independent variable first, so that's our time basis, tt, and the dependent function would go second, that's y. And there's our familiar sync function showing up. So plotting as you go is a great way to make sure that things are working out properly. One final point I'll mention is that when you're doing your development, you'll likely find that divide by 0 errors can occur. I find that adding just a small fractional value to the sampling frequency helps to alleviate that problem. So I'll leave that to you to see if you can find if that's a problem and and whether or not that seems to help. So once you have your completed math script, you can simply copy that directly into the math script node. And at this point you would want to then comment out all of these user input values so that way they can be controlled from the front panel. So you name that exactly as it appears in your math script, and that establishes the linkage between those two. You'll be naming your output something different, but supposing, just as an example, we wanted to generate the output from our sync function as the primary output. So I would call this Y. Again, that links the internal array to the exterior world. Also make sure that you select this as being a one-dimensional array type output.